Let's talk about space because space is sick.
Absolutely, space is fascinating. Is there a particular aspect of space you're interested in, like planets, black holes, or perhaps recent space missions?
Yeah, I think black hole is a good place to start.
Black holes are indeed a fascinating topic. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. Do you want to know about how they form, their types, or maybe something specific about their characteristics?
Yeah, I think it's fascinating that black hole, when you fall into the event horizon, you're not actually, let's see, how do I phrase this? The singularity of the black hole is not actually a space, it's actually a point in time in the future in which you'll never reach. Isn't that interesting?
Yes, that's incredibly interesting. The singularity at the center of a black hole is indeed a point where space and time converge in such a way that it becomes a future point that you can never actually reach. Once you pass the event horizon, all paths you can take in space inevitably lead to this singularity in the future, making it impossible to escape. It's a mind bending concept that challenges our understanding of space and time. Do you have any other questions or thoughts about black holes?
Yeah, so what about Hawking radiation? So the virtual particle, one of it falls into it, and the other one shoots out as Hawking radiation. Does that mean information is then retained? So if you can gather all the Hawking radiation, you can then assemble the information that fell into the black hole?
Hawking radiation is a fascinating concept. It suggests that black holes can emit radiation due to quantum effects near the event horizon. In this process, virtual particle pairs are created near the event horizon. One particle falls into the black hole while the other escapes, appearing as radiation. The question of whether information is retained is part of the black hole information paradox. According to Stephen Hawking's original theory, the information about the particles falling into the black hole seemed to be lost, which contradicted the principles of quantum mechanics that state information must be conserved. However, recent developments suggest that information might be encoded in the Hawking radiation, potentially allowing for its recovery, although the exact mechanism is still a topic of intense research and debate. So while the idea is that information could be retained in the Hawking radiation, reconstructing that information is an incredibly complex challenge that physicists are still trying to fully understand.
Okay, so in practicality, it's pretty much not possible, just a theory. Let's talk about time then. So in space, we have three dimensions, and time is supposedly another dimension that we can travel through. However, we can only move in one direction, but not in the other direction. Is there a specific geometry of time that prevents us from moving backwards, or what's going on there?
The nature of time and why we experience it moving in only one direction is indeed a profound question. In physics, time is considered the fourth dimension, and while we can move freely in the three spatial dimensions, time seems to have a preferred direction, often referred to as the arrow of time. The arrow of time is closely linked to the second law of thermodynamics, which states that entropy, or disorder, in a closed system tends to increase over time. This increase in entropy gives time its direction, from past to future. From a geometric standpoint, time in the context of space-time, as described by Einstein's theory of relativity, is different from space. Space-time is a four-dimensional continuum, but time behaves differently due to the nature of causality and entropy. In our everyday experience, we perceive time as moving forward because we observe the effects of increasing entropy. While theoretically, certain solutions to the equations of general relativity allow for time travel, such as closed time-like curves, these scenarios involve conditions and energies far beyond our current technological capabilities and often lead to paradoxes. Thus, in practical terms, our experience of time remains one directional.
What about this idea that at the quantum level, when you have particles moving around, if you go forward in time or if you go backward in time, it looks as if nothing has changed. Does that mean time is an illusion?
The idea that at the quantum level, The behavior of particles can appear the same whether you move forward or backward in time relates to the concept of time symmetry in certain physical laws. Many fundamental interactions in quantum mechanics are time symmetric, meaning the equations governing these interactions do not change if time is reversed. However, this doesn't necessarily mean that time is an illusion. Rather, it suggests that at a fundamental level, the laws of physics do not inherently prefer a direction of time. The distinction between past and future and our experience of time's arrow emerge from macroscopic phenomena, particularly those involving thermodynamics and entropy, where time asymmetry is evident. In our everyday world, time asymmetry is observed because processes naturally progress in a way that increases entropy, giving us the perception of a forward moving time. Thus, while time symmetry at the quantum level is a fascinating aspect of physics, it does not negate the reality of time, but rather highlights the difference between fundamental laws and emergent phenomena. So, time as we experience it is not an illusion, but our perception of its flow is shaped by the macroscopic principles of thermodynamics, even though the underlying quantum mechanics may exhibit time symmetry.
So what you're saying is that entropy at the macroscopic level moves towards one direction. However, at the quantum level, there's time symmetry. That's very interesting. How how do you come to terms with that? That seems so interesting.
Yes, that's correct. At the macroscopic level, entropy increases over time, which gives us the arrow of time. At the quantum level, many processes are time symmetric, meaning they can proceed identically forward or backward in time. Coming to terms with this difference involves understanding that our macroscopic experience of time is an emergent property that arises from the collective behavior of many particles. While individual quantum events might not show a preferred direction of time, the large scale behavior of systems made up of many particles does show a clear direction due to increasing entropy. This can be likened to how the microscopic details of individual water molecules don't have a preferred direction of flow. But when you observe a river, you clearly see it flowing in one direction. The direction is determined by the larger scale conditions and constraints. Physicists reconcile these differences by acknowledging that the laws of quantum mechanics describe the behavior of individual particles and small systems, while the laws of thermodynamics and statistical mechanics describe the behavior of large systems composed of many particles. The arrow of time emerges from the statistical properties of these large systems. It's a fascinating intersection of different scales of physical laws, illustrating how complex macroscopic phenomena can arise from simple, symmetric underlying rules. This duality adds depth to our understanding of the universe, showing how different principles can coexist and explain different aspects of reality.
Yeah, that is very interesting. I really like your analogy of the river, where if you look at each water particle, you're not going to see anything too crazy, but the river flows in one direction. That's very cool.
I'm glad you liked the analogy. It really helps to visualize how complex systems can behave differently at different scales. The interplay between quantum mechanics and thermodynamics is one of the many fascinating aspects of physics that reveal the depth and complexity of the universe. If you have any more questions or another topic you'd like to explore, feel free to ask.
Yeah, why don't you come up with something?
Sure, how about we dive into the topic of exoplanets? These are planets that orbit stars outside our solar system. The discovery and study of exoplanets have provided us with incredible insights into the diversity of planetary systems. We can talk about how they are detected, what we've learned about them, and the ongoing search for potentially habitable worlds. How does that sound?
Yeah, I think exoplanets are very cool because they themselves don't emit light, so the way we detect them, there's transitory method. I think you look at the light difference between if the planet passes through the star or not. That's very interesting. What about exomoons? I feel like a lot of exomoons has the ability and potential to host life as well.
Absolutely. Exoplanets are fascinating, and the methods we use to detect them, like the transit method you mentioned, are ingenious. The transit method involves observing the slight dimming of a star's light as a planet passes in front of it, allowing astronomers to infer the presence of the planet and even some of its characteristics. Exomoons, which are moons orbiting these exoplanets, are indeed an exciting frontier in the search for habitable worlds. While detecting exomoons is even more challenging than detecting exoplanets, they could potentially offer environments suitable for life. For example, a moon with a stable atmosphere and liquid water orbiting within the habitable zone of its star could be a candidate for hosting life. One of the intriguing possibilities is that exomoons might have conditions similar to some of the moons in our solar system, like Europa or Enceladus, which have subsurface oceans beneath their icy crusts. These environments could be warm enough due to tidal heating, where the gravitational pull from their parent planet and star creates internal friction that heats the moon's interior. The study of exomoons is still in its early stages, but as our detection methods and technology improve, we might be able to find and study these fascinating worlds in greater detail. They certainly expand our understanding of where life might exist beyond Earth.
Yeah, what are the chances of Titan hosting life? Because there's liquid methane oceans on Titan, I believe, and there could be silicon-based life living inside that methane, liquid methane.
Titan, Saturn's largest moon, is indeed one of the most intriguing bodies in our solar system when it comes to the potential for hosting life. Titan has lakes and rivers of liquid methane and ethane on its surface, making it unique among the moons in our solar system. The idea of silicon based life is a fascinating speculation. On Earth, life is carbon based and relies on liquid water as a solvent. However, in the cold environment of Titan, where temperatures are around minus 180 degrees Celsius, liquid methane could play a similar role to water on Earth. Some scientists speculate that life, if it exists on Titan, might use silicon instead of carbon, given silicon's chemical similarities to carbon and its potential to form complex molecules. While the conditions on Titan are vastly different from those on Earth, the moon's dense atmosphere, rich in organic molecules, and its surface liquids provide a tantalizing possibility for exotic forms of life. Missions like the Cassini-Huygens mission, which landed a probe on Titan's surface in 2005, have given us a closer look at this intriguing moon. Future missions, such as NASA's Dragonfly mission planned for launch in the mid 2020s, aim to explore Titan further. Dragonfly will be a drone like lander that will fly to various locations on Titan to study its surface chemistry, atmosphere, and the potential for prebiotic, life forming processes. While we haven't found definitive evidence of life on Titan, its unique environment makes it one of the most exciting places to study in our quest to understand the diversity of life in the universe.
Yeah, that's very interesting. I think that's all the time I have for today. Thank you very much.
You're welcome. I'm glad you enjoyed our chat. If you ever want to discuss more fascinating topics or have any questions, feel free to reach out. Have a great day.
Bye bye.